All right, let's dive into one of the most incredible scientific stories of our time. It's all about how we, as a species, finally learned to hear the universe. And maybe even more amazing, how we're now teaching artificial intelligence to listen for us, making our cosmic hearing sharper than we ever thought possible.
So let me set the scene. The date is September 14th, 2015. The time, down to the second, is 9:50 and 45 seconds Universal Time. At that exact moment, two enormous machines, thousands of miles apart, both felt a tiny, tiny shiver. A vibration that had been racing across the cosmos for over 1 billion years just to reach us.
Now, the official discovery paper described it with typical scientific coolness. It said the two detectors simultaneously observed a transient gravitational wave signal. But that one word, simultaneously, well, that changed everything. That was the proof they'd been looking for.
So what did they actually hear? It was this faint signal, a little chirp, that was gone in less than a second. But don't let that fool you. This tiny, fleeting sound was the grand finale to a scientific hunt that had been going on for 100 years.
Okay, so what exactly are gravitational waves? Well, the best way to wrap your head around it is to imagine space-time. The fabric of the universe is like the surface of a pond. When something really violent happens out in space, like two black holes smashing into each other, it's like dropping a massive boulder into that pond. It sends out ripples, not through water, but through the very fabric of space and time itself.
And this wasn't an overnight discovery, not even close. This timeline really shows you the patience of science. Einstein dreams them up in 1916. For decades, physicists argue about whether they're even real. Then, in the 70s, we get our first indirect hint. But it took a full century, all the way to 2015, for us to finally make a direct detection. That's incredible.
So how on earth did they do it? How do you build a microphone sensitive enough to hear space-time ripple? Well, you build one of the most absurdly precise machines ever created, the Laser Interferometer Gravitational Wave Observatory. You've probably heard of it as LIGO.
The way LIGO hears things is just genius. Okay, picture this. You take a powerful laser beam and you split it in two. You send each half down a 4-kilometer-long arm. They bounce off these perfect mirrors at the end and come back. Now here's the clever part. Normally when the two light waves return, they're set up to perfectly cancel each other out, so the detector sees nothing but darkness. But, and this is everything, when a gravitational wave passes by, it actually stretches one arm and squeezes the other, just a tiny bit. That perfect cancellation gets broken, and a little flicker of light hits the detector. That flicker, that's the sound of the universe.
And when I say a tiny bit, I mean it's just a ridiculously small number. Scientists call the distortion strain, and this is the number they measured. That's a decimal point followed by 20 zeros and then a 1. I mean, what does a number that small even mean in the real world?
Well, let's put it this way. Making that measurement was like being able to measure the distance to the nearest star, Proxima Centauri, which is over 4 light-years away, and being accurate to within the width of a single human hair. It's a mind-boggling feat of engineering.
Which brings us all the way back to that first signal. We've got this impossibly sensitive machine. It heard something. So the big question is, what in the universe could be so powerful that it shakes the fabric of space-time enough for us to feel it over 1 billion light-years away?
The data told a story that was just epic. The source was two massive black holes. One was 36 times the mass of our sun, the other was 29 times. And they were spiraling into each other for a final, catastrophic merger. They combined to form a new black hole that was 62 times the mass of the sun. But wait a second, if you're doing the math at home, 36 plus 29 is 65. So where did the other 3 suns worth of mass go?
Well, that missing mass, 3 entire suns worth, was converted directly into pure energy, the raw energy of gravitational waves. In that final violent moment, as these two titans slammed into each other at half the speed of light, the merger briefly, for just a fraction of a second, outshone every single star in the entire observable universe combined.
So, finding that first one was this huge, monumental achievement. But it immediately created a brand new challenge. Okay, we found one, but the universe is full of these things. How do we start finding hundreds, maybe thousands of them? And how do we do it fast enough to actually tell other telescopes, hey, point over here, right now?
And that is where the next revolution begins. The problem is,
The data coming out of LIGO is incredibly messy and noisy. Trying to find one of those little chirps is like trying to hear a specific person whisper in the middle of a hurricane. The old traditional methods were just too slow, and they kept getting fooled by glitches in the instruments.
This really breaks down the two approaches. The old way is something called matched filtering. Think of it like a detective with a giant book of millions of mugshots, trying to find an exact match to a blurry security camera photo. It's slow, it's expensive, and it gets confused a lot. The new AI approach, called deep filtering, is completely different. It's more like training a search dog. You don't give it a photo to match. You just expose it to thousands of examples of real signals and all kinds of background noise until it just learns to recognize the real thing. It's thousands of times faster and way, way better at ignoring false alarms.
But here's the thing. This isn't just about finding signals faster for the sake of it. Having that speed actually unlocks a completely new way of doing astronomy.
I mean, just look at how much better the AI is at telling the difference. The old method mistook almost a third of the machine's own little glitches and hiccups for potential signals from space. That's a lot of false alarms. The AI? It's wrong less than 1% of the time. It has fundamentally learned the difference between what the universe sounds like and what a noisy machine sounds like.
And this is the real game changer. The speed and accuracy are the keys to what scientists call multi-messenger astronomy. It's an amazing idea. When the AI hears a gravitational wave, it can send out an alert to the entire world in seconds. That means telescopes all over the planet which see invisible light or X-rays or radio waves can immediately swing around and point to that exact spot on the sky. For the very first time, we can hear a cosmic collision and see the fireworks at the exact same time.
But, maybe the most exciting part is this quote from the researchers who developed this AI. They said it, quote, enables the detection of new classes of gravitational wave sources that may go unnoticed with existing detection algorithms. Think about what that means. The AI isn't just faster, it might be smarter. It could start finding signals from things in the universe that we don't even have theories for yet.
So, by teaching a machine how to listen, we've gone from hearing one single faint chirp to being able to hear a whole symphony of cosmic events. We've literally opened a new window, a new sense with which to explore the universe. So the only real question left is, what else are we about to hear?